Assalamu alaikum, brothers and sisters and brothers. Master Suleiman Raheem here. Welcome. Let's slay some demons. Sisters and brothers and sisters, this is Atom Pressure Bomb Mathematics 4. We're going to talk about mathematics a little bit. We're going to go over the previous presentation, add a little more to it, because here we prove everything. If we can't prove it, we don't talk about it. If you can't prove it, we're not interested. If you're going to say Islam is mathematics, you must be able to know some mathematics, right? Otherwise, you don't know if what you're saying is correct or not. So even if you are correct, you're still a liar because you don't know you're correct. That's why you had a statement in the Quran says, if you don't bring 4 witnesses, it doesn't matter whether they tell the truth or not. If you don't bring 4 witnesses to a situation, you are a liar in Allah's sight. So if you only bring 1 witness or 2, you're a liar in Allah's sight. It doesn't matter telling the truth. Because if you can't prove it, shut up. Don't be teaching something you can't prove. Farad brought actual facts. If you can't prove it, you shouldn't be talking. You have all these talkers out there that can't prove anything they're saying. None of these religions can prove anything they're saying. There's no proof to anything they're saying. That's why I call it religion. That's why I call it, you have to have faith. You have to believe. You can't ask questions because they can't prove it. So they shouldn't be talking. If you can't prove it, you shouldn't be talking about it. Your mouth should be shut until you can prove it. We prove everything we talk about here. We don't care if you come with something you can't prove, we're not interested. We're not going to waste time with you. And we tell you, don't waste time with us if we can't prove it. We can prove it, but you don't like our proofs. That's your problem. But we prove everything we say. If we say Islam is mathematics, we prove Islam is mathematics. But you first have to know something. You can't be talking about, you can't be a blind man talking about artwork. How the hell you know it's good art now you can't see it? That's what they're doing. Talking about stuff they have no idea what they're talking about. Talking about the Bible. They tell you the Bible is sealed, so unless you unseal it, you shouldn't be talking about it. So Elijah was given that freedom to do it. He said, Elijah was told, take anything that you want, right? Just use it all. Anything you can grab hold to, use it. Help your people. So they're criticizing Elijah Muhammad. But he had actual facts to back him up. See, the supreme wisdom. And so he was looking at everything in light of that. So he wasn't wrong. He had the right spirit of it. But he did not understand the angel because it says unless he broke the seals, no one could understand it until it was revealed. And only one person in the heavens, earth, under the earth, only one person, no one else could do it but the Lamb. So that's the one you should be looking for. So let's move into this presentation, brothers and sisters. Mathematics. What is mathematics? Logic, reason, thought. See, like religion, it doesn't require mathematics. It doesn't require thought. There's not a religion, people out there, it does require thought. Because thinking people will not be religious. They say, oh, well, I'm a scientist. No. If you're religious, then there's a big gap in your thought process. Because you can't say, I'm a scientist, so therefore I know what I'm talking about religion. No, you can't say that. Because they imply that science to your religion. See, you won't do, well, that's fake. Well, then that means that you don't know what you're talking about. And that means it's not real. It's what I call reality. They don't call it faithality or beliefality. They call it reality. And that's what mathematics, because everything around you is mathematics. And tell me one thing around you that's real that's not mathematics. Don't tell me about some invisible soul that you say I have. That's only your body. You understand Scripture. I'm talking about some invisible angels that you think flying around, one on one shoulder and another one. See, because as soon as you tell you, well, there's an angel on this shoulder, angel on this shoulder, bam, bam, I just kicked their ass. So they must be awful weak. They ain't did anything about it. I just squashed both of their asses. See, it's stupid. Stupid. Okay, we're going to talk about, we're going to get into a little calculus again. I'm just going to reiterate what I said before. Calculus is the science of going from one dimension to another, going up a dimension or down. When they go up dimension, they call it integration, right? Integrals. When they're going down dimension, they call it a derivative. That means you're going from one dimension to a lower dimension, third dimension to the second dimension, or to the first, or to the zero dimension. But integrals, you're going upward, from zero dimension to the first dimension, to the second dimension, to the third dimension, right? That's the opposite. It's like you have addition and subtraction, multiplication and division. You have the two sides of it also in integration. Like it says, Allah created everything in pairs. Well, Allah didn't create mathematics. He's mathematics. He is mathematics. Mathematics always exists, always will exist. So that's what calculus is all about. So we're going to talk about it a little bit. Once you understand the concept behind it, then you can build on it. Because everything in creation, right, is either an integral or a derivative of something. When you understand what derivatives and integrals are, everything in creation is an integral or derivative of something. You're integral. That's why your body, all these pieces fit together like they do. You couldn't just put those together like, they build a robot. You're an integration, right? And in some cases, your children are a derivative of you, right? Sometimes they may be even integral to some, that's kind of, integrals are more difficult. So I'm not going to get into that. We're not going to really talk about integrals too much. We're going to touch on it, right? Because they're more complicated, but you need to understand the basis. See, because like multiplication is much easier than division. You can teach a child multiplication and they might struggle with division. So addition is easier than subtraction. See, now you have to understand thing. KV is confused. He has a weaker mind, as the angel tells you. That's why it makes him wicked, because he don't understand the creation. So if you put an elephant in a china shop, they're going to tear things up. So he's powerful, but he doesn't understand the creation. That would make him evil. Because whatever he does, he always keep on messing up the creation, because he don't understand, like playing pickup sticks. That's what makes him evil. Because you let him loose in the creation, he's going to corrupt it, because he doesn't know how it's all together. The symbiotic relationships and all that kind of stuff. He doesn't understand that. That's why the Quran says they're destroying the earth, the planet. They're corrupting it. See, because they're evil by nature. Because we built the universe from a spatial mind, and we have a spatial reality. So right here, we're going to talk about the zero dimension. Now, another thing. See, it took them a long time to even come to grip the zero. If you go back in Roman numerals, Roman times, they had no concept of zero. Roman numerals, there's no zero there. The Greeks had no concept of zero either. It didn't make any sense to them. But they had math. The mathematics still they do things, but they had a more simpler mathematics. See, mathematics is powerful, but the more mathematics you know, the more powerful you become. A person with a knife is dangerous, but a person with a gun is even more dangerous. See, a person with a bomb is even more dangerous. So a little bit of math, right, still make you be able to do things, right? But a lot of math makes you do a lot more. So they have a little bit of math, and they be able to do a lot of things. They make all spatial and all kind of stuff. That's minor to us, right? So they couldn't even understand zero. And then negative numbers, it took a long time to come down. They didn't come to negative numbers about a couple hundred years ago. So they had no idea what kind of negative number, like -5, right? Plus 3 is negative -2. I mean, they could do math like that. See? But they had to come, you have to use, according to them, you have to use negative numbers, right? The square root of negative numbers is to deal with electricity. And I think, because they don't understand tools, I don't think you need negative numbers for that. But that's the way their math works. Okay, so here, another concept, zero dimension. Now, zero dimension is a point. I put an arrow there because you can't see a point because it means dimensions mean space. That means it has no space, but it exists. They don't understand that concept. There's no concept to understand. How can something exist but take up no space? See? But that's what the zero dimension is. It's the point between two lines. So if you got an inch, 1 inch, you put 2 inches together, right? Okay, the point is right between the two. But it couldn't take up any space, otherwise it'd be more than 2 inches, right? When you put two together, it'd be more than 2 inches. But that point is it's a position between the two. It takes up no space, but it exists. It's very important. See, we're going to talk about that in a minute. Very important concept, because they don't have no idea of that concept. And we'll see why in a minute. So anyway, I just put an arrow there. That's the point. You can't see it. So it's the point between two lines. You have two lines there that are connected at where the arrow is, right? So that's the zero dimensional point. It takes no space at all, but it exists. That's the important thing. It exists, but it takes no space. Then you got a line. That's a line. That's the first dimension. Just a line. That's all. Just a line. See? Just a line. But a line has 2 points. A line has a point on each end. See? But only we're going to be concerned, that's why I got the red there. We're only concerned about 1 point. Because the other point is a mirror image of the other one, so we just forget about that one. We're only concerned about one, because the other one is a mirror image, is identical twin to the other one. So only one we're going to worry about is one. We can kind of deal with two, but I mean, it's superfluous. You understand what superfluous means, right? So that's why we got the red line there, because you got 2 arrows there, but we're only interested in 1 point. We're not interested in another point. Okay? So a line has 2 points. We're not interested, so we're only interested, it has 2 points. We're only interested in one of them. We're going to talk about that why in a minute. Here's a plane or a square. Some people call it a square rectangle. It's called a plane, mathematically a plane, right? It has 4 sides to it, 4 lines. It's made up of 4 lines. See, like a line is made up of 2 points, 0 dimension. A line is made up of 2 points, points are 0 dimension. A square is made up of 4 lines. That's the dimension below it. It takes 4 lines, right, to make up a plane. So that's what you have here. So you have 4. So yeah, but 2 are identical to the other 2. They're identical twins, so it's superfluous. We don't want to worry about 2, because the other 2 is identical. We want to worry about 2 of the lines. See, they're perpendicular to each other. See, we only worry about 2 lines. I don't know if you see my curves here. We only worry about 2 lines. Not worry about the other 2. See, because they're a mirror image of the first 2. But it takes 4 lines to make up a plane. The lines are the first dimension. It takes 4 of them to make up the second dimension. Okay. Here's a cube. Cube is the third dimension. Like your room, right? Ceiling, floor, 4 walls. It takes 6 planes to make up a cube. 6 planes to make up a cube. But 3 of them are identical to the other 3, so we don't worry about the other 3. We're only going to use 3. Right? That's the third dimension. There are no 4th dimensional objects. If they tell you there is, tell them to show it to you. There's no such thing. And there's all kinds of reasons I'm not going to explain to you now. There's no 4th dimension object. There's 4th dimensions, right? But that's talking about another kind of mathematics. You know, it's talking about variables and things like that. That's different. But geometric, this is geometry. Geometric dimensions, there's no 4th dimension geometric image. Third is the highest one you go. That's what you have. That's third dimension. It's called a cube. Okay? Cube has volume, right? A plane has area, right? A line has length. A line has length. A plane has area. A cube has volume. Okay? So I mentioned earlier the line between the point between 2 lines, the space between, not space, the position between 2 lines is a 0 dimension. So I show that. Now, when you say 0 up there, x means that's, that's how much. But the 0 shows what dimension you're talking about, right? So here you're saying 0 dimension. See, the first dimension will be a 1 there. Second dimension will be a 2 there. Third dimension will be 3 there. That's how you know the dimension you're dealing with, right? So that's it. So you see x to the 0, right? X stands for dimension, or you put d there or whatever. So that means d to 0 dimension. That's a point. See, point is x to 0 dimension or d to 0 dimension. In other words, a line to 0 dimension is a point. It has no dimension. That means 0 has no dimension. It means it has no space. Dimension means space. It means that something that exists but takes up no space. And here's a line. Remember I said a 1 there? Now 1 means a line. It's the first dimension. See? Now, we're going to talk about derivatives here. We're going down a dimension. So where's the derivative of a line? The derivative of a line, it shows you right here. To find derivative, you take over here at this point, so x to the first, the exclamation point there, we put that there to show that we get the derivative, like you use a dot or x to show timetables, right? Or a plus sign to show, x show multiplication, use a plus to show addition, and so this shows it's taking a derivative. So you want a derivative of the first dimension. So that's a line, derivative. The way you do that, you take that 1 there, whatever is there, you move it down next to the x, like I did over here, and subtract 1 from whatever was here. That's what you have over here. That's the derivative. 1, but where's this? Where's x to 0? That's a point. That means the derivative of a line is 1 point. X to 0 is a point. So, and 1 means 1 point is derivative of a line. That's what it said, man. Yeah, line has 2 points, but we want to consider one of them, derivative of a line, just that 1 point. Because the other one is a mirror image. That's how that works. See? That's what happens. So that's how you take derivative. You went down and you got a point. Take it down 1 as a point. So that's a very important concept. You'll see why in a few minutes, hopefully. Here's a plane. Now, where's the derivative of a plane? Right? We do the same thing. We take that 2 out here. You see a 2 here, the 2 here. And we take it down, put it next here like we did here, and subtract 1 from that 2. That's how you get a derivative. You just take whatever's here, put it down here as a multiplication now, and subtract 1 from there, which we did here. So that 2 became a 1, and the 2 down here is that. So now you got 2 what? 2, because x to the first, that's the first dimension. That's a line, so you got 2 lines. That's exactly what you have here. Because remember I said a plane has 4 lines, but we only care about 2 of them. That's the derivative, 2 lines. Derivative is 2 lines. Derivative of a plane is 2 lines, went down 1 dimension. And that's the process. That's where it always works. So there you got. That's how you get that. Okay. Here's a cube. Same thing. What's the derivative of a cube? A cube has 6 sides to it. Right? We only care about 2 of them. So do the same process. Whatever's here, put down here. There's 3 up here. Then put down to the x, subtract 1 from the 3, which you got 2 here. 3x squared. What's x squared? X squared is a plane. You got 3 of them. Same process. That's derivative. And if you go to school and take calculus, that's derivative. That's the formula to do it. They're going to teach you a different way. It's going to be all complicated, confusing because they're confused. But that's the way. That's how you know a derivative. So I'm showing a simple way of doing it. I'm showing you what it looks like. I'm pulling the skirt up. Look at what's underneath. This is what's under. This is what drives calculus. Now you can get very complicated with it. Like you take a brick, and you take a brick, and man, you can build a very complicated house out of it. But it's based on simple bricks. This is a concept behind calculus. Once you understand this, then you can go further. But this is what it's based on. I'm trying to pull you what's going on underneath, right? Okay, so let's move on. Okay, so here is an example. That's already this form. I'm talking about a little bit here. A line is a velocity, like you're moving along, driving the car. That's a line. You form a line. You're going on a line. You're going a straight line, right? Because if you move a curve or anything, you're gonna feel the force, right? But if you're just moving on a straight line, that's velocity. You're going 60 miles an hour, that's velocity. But if you're going 60 miles an hour, then you increase to 70 miles an hour, you just accelerate. That's why they call it accelerator, right? Because you accelerate it. You're not going at speed anymore. Now you just change from 60 to acceleration. But now if you stay at 70, you'll be back to velocity again. Velocity is that you're going at the same speed. Acceleration, when you change the speed, either change it to go higher, lower, or you go in a different direction. That's acceleration. Okay? Either way, you're going to feel a force on you. If you speed up, you're going to feel a force pushing you back against the chair. If you slow down, right, you're going to lean forward. Right? Hit the brakes fast, you're going to go forward. Right? See, speed up, you're going to feel, right? If you make a curve, you're going to go to the side, right? Because the force is acting on you. That's acceleration. You don't, as long as you're driving 60 miles an hour, you don't feel anything. But you slow down, hit the brakes, boom, move first forward. If you go faster, boom, right? Push back. If you turn, because that's a force acting on, because you just caused the force to happen, because you accelerated. That's why acceleration is force. Acceleration is force. When they say mass times acceleration equals force, all they're doing is saying is mass is just how much force it is. Like I got 5 pounds of force, so I got 10 pounds of force, 100 pounds of force. That 100 is what the mass is. See, like egg, you have an egg, you say 5 eggs. Well, the 5 is just how many eggs you got. See? 10, I got 10 is just how many eggs you got. So mass is just how much force you got. But the acceleration is the force. See? So they could just say acceleration equals force. You see? But they say your mass is 10, then it's 10 times more than if it was 1. Or if it's 100, it's 10 times more than it was a 10. You understand? That's all mass is. It's how much force it is. But acceleration is force. Because as soon as you accelerate, you're going to feel the force. You know, when you sit in the car, you drive a car, you know, once you accelerate, you move the car faster forward, right? You're going to, you're going to feel pushed back towards the back. If you stop suddenly, you're going to see forward. If you try to turn, you're going to, So that's what's happening. So you want to take the derivative of a line because that's the velocity. So the derivative is 1 point. What does that mean? Well, point means you're not moving. It takes up space. A point doesn't move. Points don't move. Lines move. Right? Velocity. But if you're standing still, that's a point. Remember I said standing still is a position. A point is a position. That means you're not moving. You're not moving. A point means you're not moving. If you have a line, that means there's distance, you're moving. But at a point, you're not moving. A car sitting still, that's at a point, it's not moving. But if it's moving, that's a line, then it forms a line. Because we went from one, when you go, what happens? When you have a line, you go from one point to another, right? You start off not moving at all, then you go to another place where you're not moving at all. And between that, that's the distance, that's your velocity. Understand that. So that's why you take derivative, you go down to a point. So when they say when you take derivative of velocity, that's acceleration. Because in order to stop, you need a force to stop. You need to speed up, you need a force to speed up. If you want to turn, you need a force to do that. So that's what acceleration is, just force. And that's why, and force is, and that's the, like when you stop, in other words, to accelerate, you have to stop going. If you're going 60 miles an hour, to accelerate to 70 miles an hour, you have to stop going at 60 miles an hour. So that's a point. That means you stop right there. You're not going 60 miles an hour again. That's a point. If you make a turn left, that means you're not going right anymore. That means, right, you're not moving right anymore. It's a point. So that's why you say acceleration, right, is the derivative of velocity because you come to a point. If you come to a point, if you try to stop, or you try to accelerate, or you try to move faster, or you try to make a turn, you come to a point that you're changing from what you was doing before. You're not doing it anymore. So now you're doing something else. See? So you stopped doing whatever you was doing. So you actually came to a stop or whatever you was doing before. I know some people understand. Say, wait a minute, I just stopped. No, you stop going. You stop going in the right. You stop going. If you're going north, you stop going north, didn't you? You're not going there anymore. That's what it means. You stop going, but now you're going west. Hope you understand. A lot of people have a problem with that and say, "Well, you mean no? You stop. You didn't stop cold. You stopped going in the direction you was going, or the speed you was going. That's acceleration. Because once you do it, you feel it in the car. You feel it. If you change, you're gonna feel in the car. If you start going north, you're going north, now you're going west. You're gonna feel it in the car when you make that turn. If you hit the brakes suddenly, you're gonna feel it. If you go speed up, you're gonna feel it. Why? You didn't feel it when you were just driving because you accelerated, right? You either went fast or slow, or you made a change of direction. So that's what it is. So when you do that, velocity, right, you generate a force. See? That's when you accelerate. So to find out what that is, you take the derivative of a line, that's your distance, your velocity, to find out what your force is. See? That when you change direction, when you accelerate, what that acceleration force is. To find out, you have to take derivative of what the velocity is, times how big your truck is. If you drive a big old Mack truck and you drive a Volkswagen Beetle, if you speed up, you're gonna have the force gonna be different because that's a much bigger thing that you're in. If you make a turn, the turn's gonna be harder in that bigger one than it would in this Volkswagen Beetle. That's what mass is, just how much more it is. See? So that's what that is right now. That's what you're seeing here. I took derivative of velocity, which is distance. X over 1 is a line. X over 1 is a line, which is distance, right? X over 1, that's first dimension, that's a line, that's distance, divided by time, that's velocity. The velocity is distance divided by time. How long you're going, how far, and how long it took, right? The distance divided by how much time. That's velocity. So I took the derivative of that, and I got the acceleration. See? At the point that you made a turn, at the point that you sped up, at the point you slowed down. Because that doesn't matter as long as you're in velocity mode, you're going 60 miles an hour, that doesn't matter. But as soon as you change to go up, speed up, or slow down, but then you take the derivative and find how much force was generated by doing that. Okay? And that's what shows here. Because over here you see velocity, you see the red ball, right? Is velocity, and see what happens. Well, something went wrong there. It's supposed to go all the way to so I must have messed up something. It's supposed to stop by the wall. So I'm not going to change, but anyway, it should have went all the way hit the wall. So if nothing would stop it, hit that wall, that means that wall would stop it. So the wall should go all the way to the end there. I don't know why it didn't do it. But anyway, it was velocity over here, now it's acceleration over here, because they had stopped. See? There's velocity over there, right? I really want to. Anyway, you saw it in the previous one. See, in other words, when you hit this, right? When you hit this, that means accelerated. So now you have this, the derivative. At this point. At this point, you got velocity is moving. But at this point, acceleration is force. Hit that wall. Obviously, I made a mistake here. Should hit the wall, but you understand. That's what that's all about. Now, we talk about it in terms of squares and things like that. Now, here's a sphere. I'm going to show you how derivative work. This sphere here, sphere, right? Now, the equation for a sphere is pi to it's the third dimension, is volume, divided by 6. That's the equation for a sphere. Pi, right? Pi is 22 divided by 7. That same equation for the angel. Angel is 22 chapters divided by 7, which is circular, means it's infinity. That's a whole other story, but I just thought I'd mention that. Pi is 20, the fraction for pi is 22 divided by 7. 22 chapters divided by 7 seals. Anyway, but that's what pi is. So pi times third dimension divided by 6, that's the equation for a sphere. But the derivative of a sphere is this. Here's a sphere, take the derivative, you get this, which results in pi d squared, second dimension, divided by 2, which is a hemisphere. Which is a hemisphere. That's where it is. You take the derivative, and this is circular. I'm talking about rectangles. Rectangles are a little different. It's a hemisphere. See? Very important. You're going to see it in a minute. Hope you understand that. Now, we're going to talk about matter. What is matter? See, they tell you matter is so small, they call it infinitesimal, which their word is saying so small, right, that you can't comprehend it. But it still takes up space. So they can't imagine that something could exist without taking up space. So they call it infinitesimal, like they couldn't figure out the zero, like they thought the world was flat for thousands of years. They can't imagine that something could take up no space, but exists. So they say, well, matter is very infinitesimal. You can't see it so small, but it still takes up space. No, it don't. Because that's what matter is. Matter is a zero dimension. See, it's all mathematics. Because that's why they messed up. Because they can't, because they say that, they can't put a mathematical number on it. So they can't put mathematics, they can't give you a mathematical equation for neutrons. They can't give you a mathematical equation for protons. They can't give you a mathematical equation for any of that stuff. Because they think it's something that they apply mathematics to. So these are things that somehow they invented mathematics to explain it. They don't understand that they are mathematics, that a proton is mathematics, that matter is mathematics, that neutrons are mathematics. They can't understand that. And their quantum physics, those things are not mathematics. Neutrons is not a mathematical equation for neutrons. It's a mathematical equation how it acts, but not for what it is. So they don't think mathematics is at the root of everything. They don't. Because they think in quantum mechanics, you got these things, right? But you can apply mathematics to them. But they don't see it. They are mathematics. So I'm going to show you. So I'm telling you matter exists, but it takes up no space. It's a zero dimension. But when I talk about integrals, that's the opposite of derivative. If derivative take you down a dimension, integrals take you up a dimension. You go up, you go up one dimension at a time, or two dimensions, or three dimensions. Depends on the integral you're trying to do. What I'm saying is matter is the zero dimension. That's the lowest dimension you get, the point, right? But I'm saying matter, the next stage is a neutron, right? And neutron is the third derivative, third integral of matter. It's going up 3 dimensions. Let me show you what I mean. Because I'm saying matter don't take up any space. That's why the whole universe could be so small. Because if matter took up space, the universe could never got small. Even Cave would tell you the universe at one time was no bigger than an atom. Now that's incredible. If you believe that, then you sure can believe what the Quran says, that the whole universe was about the size of the Earth, and then the atmosphere. So that's, if you can believe it's that small in the atoms you can't see, you sure should be able to believe what the Quran says, that the whole universe was basically the atmosphere of the Earth. See, so how could it be if everything took up space, all these atoms and everything took up space? It could never get that small as that. How can infinitesimal? It wouldn't happen anyway. So I'm saying matter is the zero dimension. It exists, but takes no space. See, you can't see it, you can't touch it, right? See, it's just zero space. Put it another way, you take a rubber band. It's 1 inch long, right? So you make it 2 inches long. Now people say, well, yeah, the rubber band got thinner. Well, say the rubber band couldn't get thinner. So where did other space come from? That means it had to be potential space, but it wouldn't take up space yet. Because you just made 2 inches, 1 inch, 2 inches, 1 inch, 2 inches. So that where was the other inch? The inch was potential space. Something had the potential to be space, but wasn't space. That's what zero dimension is. It's something that has potential to be space, but is not yet space. See? Because what you have is a universe that expands like a rubber band. It expands. And as it expands, it takes zero space, turns it into space. That's how it expands, by converting zero space into space. Zero dimension into space. Points into space. And as it goes, expand more and more and more, those points become space. And it gets bigger and creates more and more points. Because they tell you, they don't know where a neutron comes from. They say neutrons just come spontaneously into existence. Why? They come in existence because as the universe expands, it brings these neutrons into existence, because that's how it has to, by definition, to expand, you have to take not potential space and make it space. Because now you got more space. So where does space come from? It couldn't come from nothing. It had to be potential something to convert to space. And that's what matter is, because matter is just, it's energy, just don't take any space. Well, it really is not even energy, because energy, once it becomes energy, because it's inert. Because once you expand it, that means if you want to take a rubber band to pull it, you got to put some force on it, right? But if you let it go, it's going to spring back. So now you energize it. When you pull, you energize that rubber band. You energize it by pulling it, because now it's, you can feel it's trying to come back together. You energize by pulling it. If you let it go, it's going to spring back. So that's what matter is. You energize it when you expand it into space. That's why matter converts energy when you when you cause it to start taking up space. Then it's energy at that point. But when it springs back, it's just matter again. So matter energy is the same thing, like that rubber band, but now if you pull it, it's energized, it's elastic. Right? But let it go back to being what it was. Hope you understand, brothers and sisters. There you go. See? The universe expand, so it made that point into a sphere, which is called neutron. That's how neutrons come into existence. As the universe expands, it brings neutrons to existence. Not from nothing, but from points that had a potential to be space. That's what a neutron is. And that's the equation for it. So we give you an equation for that. We give you an equation for what matter is, and we give you an equation for what a neutron is. That's the equation for a neutron. A sphere. Pi d to the third over 6. That's the equation. So we put mathematics to it. That's why I tell you, prove everything's mathematics. Because the quantum scientists, they won't tell you everything's mathematics. Because they don't know that neutrons are mathematics. They don't know that protons are mathematics. They don't know that, we still don't understand gravity. Remember, gravity is still a theory. But I can tell you what gravity is. And I have not one of them ever come back. I've written books on it. Now one of them ever come back and say, anything I'm saying is wrong. But see, they can't say I'm right. Oh, that nigga, he know more than Einstein. He know how the universe works. He know math. He know better than physics. How would that roll? How would that roll? Because the master scientist, right, is Jewish. Einstein, they got to keep that going. Can't have a mind better than him, especially from a nigga. So you ain't gonna never hear them talking about, but take it to them and tell them, prove this is wrong. See, if you scientists out there, take it to them and tell them to prove it's wrong. See, it should be easy, right? They can't. See, and they know that's right, but they can't let you know that. That's a neutron. There's a proton. Proton is just neutron that spins. So all this is a neutron that spins. Neutrons don't spin because you keep pulling it, put more tension on it. If it can't get bigger, then it has to spin. So that's what happens. Neutron once coming, can't get any bigger than where it is. So if you keep pulling on it, then the energy has to go do something, so it spins instead. That's what happens. So in the center, then you got a proton. Proton is just a spinning neutron. Once it starts spinning, anything spins produces torque. Anything spins produces torque, and that's what torque is. The torque is the electron. That the neutron, because neutrons don't have electrons, because they're not spinning. But once they start spinning, then they're a proton, and when spinning produces a torque, which is electron. Now, what's electron? See, what's electron? See, electron is the derivative of a proton. See, you get back calculus again. It's derivative. You want to prove it? See, because here you got right here, there's a proton that's spinning. What's this outside of it? Outside, those are two electrons there. I'll prove it in a minute. That's the torque that's producing. It's spinning in the center, that's the proton. But I'll spin it around, those electrons. Two of them. See? Remember I said you take the derivative of a sphere and you get a hemisphere? There it is. But now we're talking about a proton. A proton is a sphere. You gave the mathematics of it. So the derivative of it would be electron, hemisphere. And two of them together, right, circles the proton. And I can prove that. It's more detailed here. Maybe I'll go into, but the point is that when you're talking about, you have a thing called electron levels. You call them scales, but electron levels. So on the first level, you got 2. On the second level, you got 8. The equation goes like this. 1 squared times 2. Right? 1 to the first power times 2. Where is that? 1 to the first power is 1 times 2. That's 2. 1 to, I'm sorry. Excuse, I'm not sorry. Apologize. I'm saying that backwards. 1, 2 to the third. Oh, let me do my mathematics. I'll make sure I get this right. It's an easy equation here. Okay. The first one would be 2. Next one would be 8. So that would be 2 to the third. 16. I'm missing something here. 2. Oh. Boy, that was crazy. Okay. The equation goes like 1 to the second power, 2 to the second power, 3 to the second power, right? 1 squared, 1 to the second power. I should have probably wrote it down. 2 to the second power, 3 to the second power, 4, so forth. Times 2, each one times 2. So the first will be 1 to the first, second power is still 1, if you understand mathematics. And you multiply times 2. Well, that would be 1 times 2 is 2. The next would be 2 to the second power, which is 4. 2 times 2. Times 2 would be 8. Next would be 3 to the second power, which is 9. 3 times 3 is 9, times 2 is 18. So therefore, you have, on the first level, you have 2. On the second level, you have 8. And third level, you have 18. So that's the way these electron scales. I know it's a little complicated. I should really do more picture, but it's kind of complicated to present this. But you have, on the electron, you have different levels. So on the first level, you can put 2 electrons. But electrons are the same size. On the next level, you put 8 because it's bigger space. So exactly 8 would fit there. On the next level, exactly 18 would fit there. And it's a simple equation. And the only way that would happen is they would have to be hemispheres. They give you electron little dots going around. That's wrong. That's wrong. See, because they don't know what an electron looks like. They've never seen one. They can't never see an electron. Their microscope's just not that powerful. They've never seen an atom. Part of the reason why they can't see it, and I'll say this in passing, we see photons. That's what we see. You don't actually see an object out there. You see the photons that the objects hit you. That hit your eye. Or a chair, right? Photons hit the chair. It excites electrons. Electrons release photons. Photons get your eye, and that's what you see. You actually see energy. You never see. In fact, everything around is energy. Even things you think is solid, because we're energy ourselves. So we think everything is solid, but everything is energy, and we energy. We like. Because they're talking about spirit. You are spirit. But if you had two spirits, they touch each other, to them they'd be solid to each other. Two spirits touching each other will be solid to each other. And we are spirits, if you understand Adam's word. If you look at Adam, there's this little Adam, and all the space. I mean, we are spirits. So there's nothing could be more spiritual, more spirit based than we are. But since we all are like that, and everything is like that, we think we call it solid. SOLID. But when you look at a something, what you see is it absorbs the light from the sun. The protons, the atoms absorb the light using electrons. I'm not going to science that. But the photons are like electrons. They're almost identical, but there's a little, they can absorb. That's another story. Anyway, the electron absorbs the photon, right? And if it absorbs it, it keeps it. That's what black is. Black absorbs all the photons from the sun. So that means you don't get any photons from it. That's why it looks black. It's the absence of photons. That's what black is, the absence of photons. You're not getting any because it's absorbing all of it. But white reflects it all. It doesn't absorb any of it. So it reflects also. You get all the photons back and everything else in between. So when you see like green grass, right? Well, that's not the color of it. Those are the photons that it doesn't absorb. Those are just the photons it didn't absorb. It absorbed the red ones, it absorbed the yellow ones, it absorbed everything else. It just absorbed the green ones. So the green was reflected back, and that's what you saw. So to you, it's green. So that's another story. We'll talk about it more complicated another time, right? More talk about it, maybe explain another time. Anyway, that's derivative. I'm putting numbers on this. Derivative of a spinning neutron, which is a proton, is electron. Put numbers on it. Derivative. Notice everything is derivative or integral to something. And so far, I've been showing you that how neutron is an integration of matter, and electron, right, is a derivative of a proton. So, hope you understand. So I'm going to give you a little example right here. Fusion. Now, there's a proton here. Fusion, you have two processes, fusion and fission. Fusion means you put two things together. Fission means you pull them apart. See, fusion is pressure. Fission is tension. Tension is opposite of pressure. Tension pulls things apart. Pressure pulls things together, push things together. So fusion is pressure. That's what you have in the center of stars. You have so much pressure that can force protons together because they resist being pushed together for all kinds of reasons I'm not going to talk about here because of charge and stuff. I can give you mathematics if I have videos out to explain it. Anyway, but it pushes them together. Right? Because by spinning, they have that torque, they have a charge. Neutrons don't have a charge. You can put two neutrons together, they have no problem. The protons do because they spin and they do that force, that torque. So it's hard, you can't put them together. It takes a lot of force to push them together. So here it is, they're fused together. But they won't stay like that. Like you take two magnets on the same pole, you push them, you got to hold them there. Because as soon as you let them go, they're going to come back, they're going to fly back apart. Okay? So, I don't know if I'm not going to read this. You can read it on your own time. I'm not going to play it. I'm just going to move on. Fusion. Let's move on here. Now, here's two protons here. Now, I'm showing you, I'm like putting them on a rubber band or something to try to emphasize what's going on here. This is normally, that's where they would be, they're happy. As long as they separate like that, they're happy. No problem. See? They have two as long as it's probably this effect. But you try to put them close together, they're going to resist. You try to put them close together, they're going to resist. So I'm putting those yellow things there to try to give you an understanding of what's going on here. See, they push together. But see, if those rubber bands in there, those rubber bands are real tight. So the rubber band will try to pull them back apart again. See? So that'd be one tension unit, try to pull them back apart again. That's why I put those like yellow rubber, because if there's rubber, they push them, they're going to try to pull them back again. They're going to try to pull them back apart again. So unless you hold them there, they're going to spring back to the position they was in just now. See? Unless you force them, unless you hold them there, they're going to spring back, right? So they're going to push them together again. And what you think? They're going to spring back, right? One tension unit, they're going to spring back. Or are they? See what happened there? That's that force trying to pull them back, right? But what happened instead was that's the same force it takes to make a neutron. Remember I said neutrons take matter, you got to, it's tension, put enough tension on it, it converts to a point, to a neutron. That's the same amount of force that if you try to push them together, that's enough force that would generate two neutrons. If they're there long enough, if it generates those two, there's nothing pulling them apart again because they absorbed that force that was pushing them apart. They absorbed it. That's why all atoms have to have neutrons. That's what keeps them together. They don't know that in quantum physics. They don't know why a neutron has to be there. They say neutrons hold protons together. They have no idea. They got all kinds of weird theories, right? But that's what happened because you made matter points, because matter points are everywhere, all over the universe. So you cause two matter points, right, to turn to neutrons. So that absorbed the energy that was normally pull them apart. So now there's nothing pulled apart. So they stay together now. That's a helium atom. It has two protons, two neutrons. Hope you understand that, brothers and sisters. I hope one day, hope to go into more detail with this. If you have any questions, let me know. Okay, let's get to this and then we wrap up. A triangle. Most of Cave's mathematics is built on triangles. Triangles are very powerful. This is very powerful. Like I said, if you take a triangle here and you take this side and multiply it by itself, so if this side is 5, say 5 times 5, if this side is 4, 4 times 4, and you add this and this together, it's going to be the same size as this. A plus B equals C. It's powerful. That's powerful. And so much mathematics is built on that concept. They call it the Pythagorean Theorem, like they just visited. See, it's a lot more in here. I'm just showing you this part. A plus B equals C. Vectors from that concept. There's another powerful form of mathematics. Vectors. See, they shift these around in this form, the same as this, just shift it in this form. That's what a vector is. If you have applied force in this direction and force in this direction, you're going to get a resultant force in this direction. Like you have a car, two cars colliding, right? It's going to push them off in this direction because that's what these vectors say. You have a force in this direction, force in this direction. This is going to be the resultant of the force of two directions. If this is smaller, right, then this arrow is going to move more down this way. The smaller this get, the more this arrow is going to move more down this way because it's most of the pressure is coming from this side, force coming this side, and less from this side. But if this gets longer, then it's going to start moving that way because there's more force coming from this point. But right now, it's equal on both sides, so this is coming in that direction, right? At that angle. That's all vectors are. A plus B equals C. Very powerful. Very powerful. But a lot of math is based on that. Once you learn vectors, boy, that's powerful. Learn vectors is powerful because you're dealing with forces on a very basic level. This means this force plus this force equals this force. Just add forces together. It's addition of forces. That's what vectors is. Addition of forces. You got the multiplication of forces. You got the division of forces. You got division of forces. You got all kinds, right? The integration of forces. But this is the basic. This is the addition of forces. That's what vectors are. Trigonometry. Again, triangle. But it's based on the fact that every triangle, no matter what form it is, right? We've got three sides, they connected, straight lines, is going to equal 180 degrees. Every triangle, so that's what trigonometry is based on. It's based on the fact that it's still trigonometry, still triangles again. I say almost all that mathematics is based on triangle. Every triangle, no matter what kind, so in this case, right, it's a 45-degree angle. So 45 plus 45 is 90 plus 9 is 180. Because this is right angle is always 9 degrees. These two are equal. So 45 and 45. This one is a 60-degree angle. So this each was 60, 60. That's 180 degrees. Every triangle is like that. So that's what they use in trigonometry. Sine, cosine, and tangent. That's all based on the fact that every triangle has 360-degree angles. 360 degrees of angles. Right? I mean 180 degrees. 180 degrees, not 180 degrees. Half of 160. Half of 360. 180 is half of 360. I'm going to explain it in a minute. See, here's an idea of trigonometry. See, here you are in LA, right? Here you are in New York. So you got one person here in LA, one person in New York, and both of them draw an angle right towards to the sun. Both of them. See? Now, he knows how far it is from LA to New York, maybe 3,000 miles. He knows it's 3,000 miles, right? So, and he says, okay, what degree are you getting? What's your degree when you try to point to the sun? What degree is this? He has got in LA. So what's your degree? You put it together. So you know this degree has to be what's left. So if this degree happens to be 30, this has to be 30, right? That's 60, right? That means this has to be 120 degrees here. That's equal 80 altogether, 180 altogether. So they know that. Then they can tell how far this distance is. If they know how far this is, because they know this triangle only could have that degrees, had to be so certain size. So that's how you know how far it is. See? He said, what's your degree here? How many degrees you got here? When they said angle to the sun, what degrees, right? From this line from New York to LA. That's how you do it. That's trigonometry. Angles. So you can tell how far a star is without even going there. See? Now, this is what I was talking about, angles. Now, if you take this circle here, that's 360 degrees. But if you take each piece of the circle and divide it in 4 parts, see if you add these 4 parts together, they come back to a circle. See these 4 parts right here? I broke them up. So that means each one of these corners, right? You divide 360 by 4, which is 90. So each one of these corners are 90 degrees. Each one of these corners is 90. This is 9 degrees, this is 9 degrees, this is 9 degrees, 9 degrees, right? But we only want half, but triangle is only half of that. See? This triangle here is only half of that. So that means the triangle, instead of being 360, be 180. Because from here to here is 180. I mean, here is 90. But this is only 45 now because you split half of it. You only got this much of it. You only got this much of it, 45. So 45 and 45 is 90, 980. That's where you get that from. See? Because this whole triangle would be 360, but you only want half of it, which is this whole rectangle would be 360, but you want half of this triangle. That's where you get the degrees from. Okay, brothers and sisters, hope you understand. I thought I'd go a little more, try to get a little physics here. Because if we say everything's mathematics, we have to prove it. Because if I couldn't prove it, I wouldn't be saying it. I'd be saying, well, I think it's mathematics. I was taught it was mathematics. But I wouldn't be saying it is mathematics. Because I'm saying it is mathematics because I can prove it. Okay? And if we can't prove, we don't deal with it. We're not in belief matrix here, right? We're not in Jerusalem, right? It took us out of Jerusalem, put us in Jerusalem, illusion, the land of illusions. If you can't prove, we ain't interested. We deal with facts here, period. And we take script. They say, well, how do you know script's a fact? We can prove script's a fact too. So maybe I'll go into more detail about that. See? But so far it's been right. Everything it says so far, at least once you get it right. Okay, brothers and sisters, hope you understand. Hope you understand, brothers and sisters. See? Trying to be helpful. Okay, I think that's it. Pretty sure that's it. Okay. Is there anything else here? I guess that's it. Okay, assalamu alaikum.